Yeah, let's start. The topic today is Intro to AI World, or how neural networks work. So here, what I'm going to tell you today. So the first one is basics and mechanics. The next one is basic elements of neural network, activation functions and their role in the neural network learning process, and what is gradient descent, deep learning, parameters and hyperparameters, and why are neural networks only now becoming popular. So yeah, let's start with the first one. So yeah, as I said already, the topic is intro in AI world, but it's not really about AI. It's about like subcategory of AI, since AI is like very very like wide field in like it's just a wide field, and the really neural networks are very deep there. So in AI includes machine learning, and on the machine learning includes neural networks, and then neural networks includes deep learning and deep neural networks. So yeah, really neural networks and overall machine learning uses the following approach. Is like data, calculations, and algorithm. The first is we need a lot of data that will be calculated using by some algorithm that I will tell you today. Yeah, let's define basic elements of neural network. Let's start with X. X here represents data. It's like not just data, but feature data. It's some features that data may have. For example, if we talk about houses, it can be price, location, etc. Then we have output, Y. The output can be like very different. It depends on the purpose of the neural network. So how transform X into Y? Here we need like this element neuron or node of neural network. So yeah, how neuron transforms X and Y? As you can see, it's already have some shape, its function, and using some function, we get some results. For example, for x1, it's y1, y1, and etc. And as you can see, we can like draw a line here and get this linear function. It has some biases. It's not really like exact numbers, but just for example. And yeah, as I said already, it's linear function. But as you might know or hear about neural networks, that they are like the idea of them is to make it so how the human's brain work, and human's brain is not really linear in processing data. So, for example, yeah, processes in real life are not linear. And for example, let's imagine that we have images of cars, and like we want to like categorize them, like classify them, if it's a car on the image or not. And for example, the first image is car. We see wheels, recognize form, and etc. And for example, the second image is also car, but it's a bit different. it like imagine that it stands on the carpet, and on the background there is like a teddy bear, and we know that it's car, but it's not real car. It's like a toy car, and this is like not this linear process of thinking. It's like some edge cases, not just edge cases. Yeah. So here we need to make the neural networks work as human brain. We need to bring some non-linearity, and here we come to activation functions. It's non-linear activation functions. Activation function basically represents the neuron in the neural network. So yeah, there are some examples of activation functions that commonly used. It's sigmoid function, it's a rectified linear unit function, it's leaky ReLU function. There's also many others like Tang functions, softmax, and etc. They have like their purposes. I will tell you a bit later about each of them. Yeah, for now it's just like, for example, let's take a closer look on sigmoid function. So here what it represents that for some x value, the function, the output will be from 0 to 1. So you might see that it's really it's like classification on true or false, like Boolean value. So yeah, here that sigma of that is like the output, and that is wx plus p. It's linear function that that I told you earlier. And yeah, this is the function of sigma, how it looks like. It's 1 divided on 1 plus exponent powered minus z. And if talk about its intuition, so for z, very, very, very large z, it will be always 1. So yeah, it's like as on function here. And yeah, this is how it looks like. It's like 1 divided on 1 plus exponent powered minus infinity. It's like that, and then 1 divided on infinity. It's like almost null, approximately null, and 1 divided on 1 is 1. And the same is for when z is very, very, very small number. It's like infinitely negative number, and here's like 1 divided on infinity, and it's approximately 0. So this is how it works. Yeah, this is like z is dependency, and y is output. But what about w and b? Which value should they have? It should be like 2, 3, or 3, 8, or 1, 0. It will be just x. Let's take a closer look on this one. Here we come to gradient descent. I will tell you about this process. Okay, we have y as output, but really we have two outputs there. The first one is expected output. It's like what we expect to get from the data we give to a neural network. And the second one is why that we really get from neural network is calculated one. And here we come to two more very important functions. The first one is loss function. It's like it's two measure functions. The first one is error measure for a single example. So we have one example of data, and we get one and we have one expected data, expected output, and we have one calculated output. And this we will calculate how what's what the probability that error appears in this. And cost functions is also error measure, but it's not for a single, but it's for a set of examples. And yeah, it's like arithmetic mean of the loss functions of all examples. Let's take how was the definition of loss function. Usually, when we talk about error, we can use like root mean square. It's root mean square. It's like the difference between calculated and expected value powered 2 and divided by 2. And it looks like something like this. It's non-convex function. It has like several minimums, not only one, and it's not really useful for learning process. You will see now why it's not. And for sigmoid function, there were like there is another function, another definition. It looks like this. I won't show how it was created, but it really has the same intuition as this one. Something like this. If y is 1, we have a minus log y y hat, and if y is 0, we have minus log 1 minus y hat. And this is convex function. We have one minimum here, one global minimum. So we can know the place where loss function, like the minimum, the error is minimum. So the idea here is to make, to have those dependencies have the same, such values that function is minimum, has minimum value, has minimum error. Yeah, let's take a closer look. Basically, this is a cost function, and the dependencies are W and B. It's not Y and Y hat, just because it's a set of examples. It's not one. That's why the dependencies are W and B. And if you take a look on the function and on this graphic, you can see it's like I don't know how to name it. It's like, okay, you will see. You see. So yeah, the minimum of the function is here. It's like intuitive. And yeah, for example, we have some W and B defined. I don't know. It can be like a 1.5 and minus 1.5, and the current value of cost function is here. So yeah, but the goal is to make it so it's here in the minimum of the error. So what we're gonna do is to move there, like step by step. And what it is, it's basically gradient descent. It's like moves on the gradient. And this move represents here. So basically it's alpha. Alpha is learning rate, or as I imagine in my brain, in my thoughts, it's like the length of step. And derivative, its direction on some point of the function. So yeah, there is like a picture of gradient. It's like this red dots are derivatives on each of these point of the function, and we can like do some projections. It's not really it's not really like it should be, but for better understanding, we can do it like that. And like this is 3D, three-dimensional view, and there is like two-dimensional views, and we can also see like derivatives on two-dimensional functions. And for example, on this point, the direction is this one. On this point, the direction is on this one, and etc. It's for a W and for B. And this is formulas. This formulas how derivatives are presented for B and W. And this is what like the step is look like. It's basically we just move, like we get rid of, like we move on from B to B minus alpha dB. We do the step here and here as well. I want to tell you about derivatives. There are like list of already defined derivatives on some very like good known functions, and yeah, you can just take search for derivatives and learn it yourself. The idea is to use derivative as a direction on move to the minimum of the cost function. Yeah, so basically the algorithm is next. We start, then we go to like to condition. We check is cost function is minimum. Next is if it no, we move W, we move B. So it's like we change, basically we change angle of the function and also bias of the function. So we check if we find the right place. We try to find right place so the outputs are close to this function of the line. Then when we moved, we try to we check again if the cost function is minimum, and we repeat this process till the error is minimum. And if it's minimum, the learning process is finished. Yeah, you might ask what the minimum is. It's not for this topic, but basically it's what you defined minimum. It can be 2% of error, it can be 5% per error. It depends on purpose of your network, neural network. Yeah. Basically, that's it. What was I told you about, like very simple neural networks with one neuron with one activation function. So what is deep neural network? Basically, that's it. It has more nodes. It has layers. Layers and nodes. It like the number of nodes different for layers. The amount of layers also can be different. It depends on you. So yeah, basically, what's the common part here of simple NaN and deep NaN is this one, or even I would say this combined with this. It will look will look the same and will have the same output. It's like visible part of the neural network. We know about input, we know about output. That's why this part also known as hidden layers, just because we don't know what's happening there. We don't know which values, which outputs each of them has. We don't know which weights, which W's it has. We just know the result, the end result. This is deep neural networks. So let's transform. Let's divide the process of transforming simple neural networks algorithm to deep neural networks algorithm. I try to divide it on small steps, but reasonably small steps here, just because it will take too much time, and I want to make it in time. If I will tell you all details. So yeah, as we already defined, for simple neural network, sigmoid function is look like this. But next we define that we have m examples. So it's not only one example, but some amount of examples, some set of examples. We have n nodes in one layer. So it looks like input, then some nodes, then last activation function, and output. So what we gonna do here is what we need here is vectorization. Basically, we're gonna since we operate with this number of numbers, we need vectors and matrix there. So yeah, basically using vectorization, this formula transformed to this one. It's very similar one, but the only difference, oh sorry, I forgot sigma here. It should be sigma function. But the difference here is that all the values becomes vectors and matrix. So z is vector now. W is also vector now, but yeah, it is this letter T is transposed. It means that the vector is change its direction. It's when it's simple vector, and then if it's transposed, it just becomes from vertical to horizontal and vice versa. If, for example, W is horizontal vector, it becomes vertical. X, it's matrix. The row represents examples, and N represents nodes here. So yeah, it's M examples for N nodes. And the formula is X matrix W transform plus P, it's Z. Why B is not vector here? Just because, or not matrix, just because P is always the same number for each node and for each example. That's why we can just make it a real number. Yeah, and this is formula for one layer. Let's take the next step. One layer and I layers. So yeah, it's how it looks like for one layer. it's taken from the previous slide, what we do for I layers. Basically, we have a loop from 1 to number of layers. And so the formula transforms to this one. So output is a sigmoid value of C of this layer. And this is how Z calculates for the current layer. And yeah, for like X, you can take, so xi, it's output of the previous layer. So for example, for the first layer, x can be represented as x0. It's like very first set of examples that you provide to neural networks. And then the next one will take the output of a previous layer as input. And yeah, I just like in the loop, it takes for the output of the previous layer to the next one. Yeah, it was about activation function, but what about gradient descent? The intuition is the same. We start with one dependencies. Then we make factorization. It becomes like vectors. Yeah. About these formulas, I also want to tell you about how it calculated. Why are they like look like this? But just take it like true, true values, true formulas. And for deep NN with I layers, it's the same. It's loop, but in opposite loop. It starts from the last layer and go to the first layer, and it calculates derivatives for each layer and make like moves for each layer. So yeah, why it's here? Why it's not I but I minus 1? Just because for the very first, like very last layer, it's calculated a bit different. It takes like yeah. I heard something.
No worries, just a comment. Go on.
Yeah. Let's go further. Yeah, basically that's it. It's a whole algorithm. So what's next? We have output or input. We have algorithm. We have metrics, measure errors. Should we just wait? Just give neural network what it needs, like set of examples, and wait the result? Not really. We can control the process here. For example, parameters that are W and B, usually they are initialized randomly, just random numbers, and then they transformed into their true numbers while learning process. What we can control here, what we can set is hyperparameters. It's alpha, it's this learning rate, the length of step that will be taken. The next one is number of hidden layers, how many layers the neural networks will have, number of units, how many units each layer will have, activation functions. Yeah, you can choose them also, and number of examples in training set that will train the neural networks, and many others that I won't tell today, but probably sometime later. I don't know. Yeah. And the question is, why to choose the activation function? Why just not use one that I told you about, like sigmoid? So yeah, as I said, sigmoid function is basically for binary classification, but it also has like each of the activation function has its own issues, and a new one that was like that to fix issues that has the previous one. So sigmoid was the first one. The issue that it has basically it's binary classification for non-binary, but for some values there is like softmax activation function. You can search and read about it, what it does. So yeah, for the sigmoid function, the issue is that some points of the function has like the function has some points where gradient is almost zero, so there is no angle interaction, and that's why the moves can be really slow, and that's why the process of learning can stop somewhere, and be very 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 slow and take like years to learn, like for neural networks to learn. That's why some very smart people come up with ReLU function. It's a rectified linear unit. Basically, it's about that for positive positive input, there is constant constant angle, constant direction, good direction for gradient descent, and that's why the learning process is fast. But it also has like their issues. Is that because for negative numbers that are really really rare, it will return zero, and that's why some activation it can make some activation functions useless, and the process of learning is also becoming slow. That's why as a fix for ReLU, there is leaky ReLU function. The difference is that for negative numbers, it's not zero. It's like very, very, very small number. It's like 0.01 of input of x. So yeah, it fixes ReLU issues with negative numbers, but it also has its own issues. That's why there are many other activation functions that can be chosen. So yeah, why are neural networks only now becoming popular? First of all, yes, you might already know that neural network concept was created like in the previous century. It's like in 20th century, but it's only now gives some results. The first reason is that a lot of data accumulated by time, especially like the past 20 years. There was like the era of internet, the era of data. That's why there are a lot of data now. And as I already said, like in the beginning, the data is one of the operand of neural network. The second is that the computer power was increased. New technologies, new laptops, new servers, and etc. They're more powerful. The the third thing is really like the second, but I put it separately just because it's a really important thing. It's like CIMD was added to GPU and CPUs. It enables processing of multiple data with a single instruction. So now for computers, it's easier to perform operations with matrix and vectors. And the last one is that some more solutions, new solutions to problems related to neural network training, such as bias and variability problems, and other difficulties in achieving a global minimum were created. Yeah, if summing up, I told you about basic elements of neural network, data processing, learning process, what's the difference between simple neural networks and deep neural networks, and introduce you some like very, very light tuning process. Yeah, and basically there are a lot of existing neural networks, and it's like very, very small probability that you will try to create your own. You will just use an existing one just because it's trained well. It has a lot of data already. So yeah, this information for you just to understand how it works, so you can like apply your knowledge when you will try to optimize neural networks or solve other issues. When, for example, your like input is not giving your right output. Yeah. And yeah, what's next? As I told you about like basics about neural networks and deep learning, the next step is to find out what's optimization algorithm it has, what is fine-tuning, just because there will be more and more hyperparameters for optimization algorithms, and also regularization processes that will help you to get rid of biases and variance. It's like a problem of overtraining and a lack of training of neural networks. And I think that's it.
Wow, thank you. I haven't seen that much formulas since my university studies. It was really impressive. Guys, if you have any comments, any words you have after listening to this super curious material, let me know.
If I still want to create my own neural network and train it on my data, what languages, what tools should I use?
I think it's like Python. It has very good leaps, math leaps that will calculate derivatives for you, that will calculate, make operations on vectors and matrix fast. Probably there is like the similar leaps on other languages, but as you know, Python better suits here.
I can add here, actually. Yeah, in Python there's a Keras library. Keras, and inside it there's also multiple libraries inside. I'll send the name in the chat. It provides you. Yeah, in the chat I sent it. So it provides you not just with functions for calculating matrices and calculating backpropagation changes, like, for example, NumPy and other mathematical libraries. This one provides you with functions to provide the whole layers. So basically, you just define declaratively that, oh, I want this layer connected to this layer, connected to this layer. This is input, this is output, and your whole model is ready. So basically, you don't need to do anything. You just need to design your solution, how you want your model to look like. Declaratively, in less than 10, 15 lines, define it. Compile, train, like compile by compile function, train by train function, and you can use it.
Yeah, that's why I said that it's not really like important to use to create your own model. It's not really important to know how it works, but for better understanding, for better like usage of optimizations and other things, it's good to know.
Is there an industry standard for model files? For example, if I download a model from Hugging Face, like some random normal neural network model, what file format would it be and how it looks? Do you know?
File format for what? For model?
For model, yeah.
I think that's model. As I know, models are stored in GPU or CPU. They're not in file file format, but I'm not sure. I guess that the hyperparameters and parameters are stored in GPUs and CPUs for better performance, and they have like their architecture, how to store it like in different places and connect to each other. But probably I didn't get the question right.
So yeah, like this is how it's done in like runtime when it works. When it's stored, it's highly dependent on the implementation. For example, if you want to download Keras model, it will be in one file format, most probably several files with certain file structure. And if, for example, it will be in R and library for R, it will be in completely different format. Yeah. So there's
So
no.
Keras has its own format.
Yeah. Like as I described, when you create a model, you can also save it, like by save function, and it will create the structure and everything needed to export and re-import it later.
Yulia, you're muted if you.
All right. Sorry. Okay, guys. Do you want to add anything? Any thoughts you had during listening the meetup? Or thank Nastya once again.
I wanted to say thank you to Nastya because I mentally returned to the moments when I was learning about this stuff. And the funniest thing is that this is the stuff that I learned for 4 or 5 times because it's always like when you try to get into AI, it's always like this is neural networks, this is their functions, this is matrices, this is backpropagation. So it's like, oh, I returned to 2018, 2019 to 2021.
So the learning never ends, right?
Yeah, I'm learning the same thing actually.
Let's discuss transformers some next time. If somebody wants to prepare, or you, Nastya, plan to prepare next meetup. About neural networks or about
For
AI?
transformers, we need to know about how LLMs look like, and LLMs is basically, or I forgot how the name, natural language, natural
Processor?
language, yeah, NLP, and it's different topics. So LLMs is on top of NLP, and yeah, but probably we can just have like very separate topic from this, the whole. Yeah.
Yeah, it would be nice if you think how to continue the topic and prepare more speeches on this topic. And I think it will make it a good blog post. I'm planning to wrap it into a blog post. Yeah. Okay, so we are ready to finish. I don't know the topic of next meetup, but I'm sure when Andrew returns from his vacation, he will notify you guys on Slack. Thank you, Nastya. Thank you, everybody, for joining, and have a nice week.
Bye.
Bye.
Thank you. Bye.
Bye.